Hi. Can you all hear me? Oh, let me try. Good afternoon, everyone. Good afternoon, everyone. Okay. Yes. So on Monday we have. Where is my PowerPoint? On Monday we have covered about the dynamic programming. Sorry, let me find out. Okay, never mind. Okay, sorry. So on Monday we have covered about the dynamic programming, and I have talked about two problems, very classic problem. Okay, Fibonacci is the one I introduced to use on Monday, and then the road cutting is one. I would say is a kind of a 1D dynamic programming problem, because the factor is depend on the price. You can 1 cm $1, 2 cm $2, 3 cm $8, and so on and so forth. From that, you need to decide how to cut the road. Then this problem is one of the very classic dynamic programming problem. Another one I introduced to use is a 2D problem, which is also very famous, MP hard problem, which is where is it? 0-1 knapsack problem. 0-1 knapsack problem. And this one have two factors you need to consider. One is the size of the item. The other one is the value of the item. So you need to trying to maximize the value. At the same time, you need to keep the total size of the item less than the capacity of the knapsack. The knapsack capacity. So it's like you can select or not select. So the solution in the end is you trying to build all these dynamic programming problem. You find that it's trying to build a table, and then from that you trying to fill out the table and solve the solution, find out the solution you want, or there's a top. This is the bottom up approach. Top down approach is in the reverse. You want to solve this problem, you want to know the answer of this, your you have I item and the capacity is J. You want to find this one, you need to backward find the answer when without the I item, and without the size, reduce the size of the I item. You -1 and minus the size of the I item. This one plus the I item, the value of I item. Or you need to find another one. Either this is the answer, or the answer is without the I item. Simply without the I item. That's mean it's like, in short, it's like you're trying to solve the problem, is always trying to think that you want to include the I item or exclude the I item. Then you slowly build out the table. And you can top down or bottom up. Both. There are two ways. Dynamic programming, there are two ways. Sometimes bottom up is better, sometimes top down is better. So that is how I introduced the dynamic programming problem on Monday. So this one, you just fill out the table. If I want to know the capacity is 5, I have 4 items. And then these are the 4 items, the size and their corresponding value. So I slowly build out the table on Monday. Then in the end, I find out the answer is $37 is the best, the maximum value you can have with the capacity of 5. That is the dynamic programming. So the problem, if you try, I think earlier you have seen, I think you have 4 items, is 2 power to 4. You can select and not select, select or not select. So they are 2 power to 4 combination. If you try all of them, then the complexity is 2 power to 4. But actually, by build up this table by the dynamic programming approach, you can improve by a bottom-up approach. You can improve to n times c. You just fill out this table. So it's n by c. Yeah. But however, this one is still, I have to highlight to you, is like, of course, compared to 2 power to n, you improve it, but it's still n times c, and c can be a very large number. If c is very large number, the time complexity of this problem is still not cheap. Yeah, so this is one of the very well-known computer science problem, 0-1 knapsack problem. Okay, so this one is what I introduced on Monday. So today I trying to move on to today's topic. Is that matching? Oh, this one later question. Okay, so today I will talk about the matching problem. It's another interesting topic. I think I will use today and Monday to talk about it. So probably next Monday and then the next Wednesday, I will give an overview or clarify your doubt. I guess maybe next Wednesday I probably will use a Zoom to let you clarify, or consultation times or something like that to clarify your doubt. Maybe before I start this lecture, any idea how to begin? Okay, let me for the assignment, there's one question is about the city population. Okay, first in the given input, I already give you the number of city. I have given you the population of each city. That is in the input. Then after that is followed by the path or the connectivity between the city and city. So the question already told you that. You have n city, and two city always have any two city always have a unique path. Yeah, always have a unique path. And then it's a tree. There's no cycle. Because there's no cycle, if you have learned in the previous tutorial, the breadth search, all this, you should realize that if your graph is a tree, there's no cycle, such a graph, you select any two city, it really give you a unique path on it. Because there's no cycle, you wouldn't be able to find the second solution. Right? And second thing you need to realize that such a graph have a characteristic is like they only have, if you have n city, then the number of edges is n minus 1. Is n minus 1. You can try to draw any city. You will find that is always the case. Yeah. So after I give you the population, the next n minus 1 pair number are the city, the connection between two city. And then after that, the 1, 2, 3, the number of city, population, the root, then the next integer number is the Q. Then next one is I give you Q query. So I will start asking you, the query is given to you, like let's say if Q equal to 5, their next 5 line is telling you it's a query. That means each query you have 3 number. The first 2 number I give you the ID of the 2 city. Yeah, city U and city W. City U and city V. Then followed by the third number is W. Is like we need to find between city U to city V, or city V to city U. Definitely there's a unique path. Along this unique path, how many city, their population is at most the third number, the W, the third number. So that's mean they're not more than or equal to that number. So you just find the path and then find along the path what is the corresponding, which one is more, then you make a count. Yeah, if it's less than or equal to the given number, then you increase your count. If it's more than that, then you not count. So including the U and V. So how to do it? This is something I let you think about it. You want to find the path, you count. But I have highlight to you all that there are 4 test cases. The first 2 test case is very small, only 10 and 50 CT only. I think if I remember correctly, a very small number. So you use whatever data structure, whatever approach. As long as you find the path, you just check along the path, you should be able to find out. You can easily solve it. Is when you go to the third test case and fourth test case, you will find that I trying to give you tens of 1,000, 80,000 data. The 80,000 CT, your N is 80,000. At that time, then you need to think about how to optimize your code. Yeah, to improve the efficiency. You have I already trying to give you as many time and memory to run, but there's a limit for the system. You only can run up, each test case you only can run up to 10 seconds. And I think the memory I increased to 1 GB per, yeah. So for each test case you only can run up to 1 GB. Yeah, then you try. I would say that's what the tips I can tell you. Okay, so let us start the today, man. I would like you to go and think about your solution, and think about it is like you think about it is like I have to emphasize the question again. You take notes that it is a tree, and there are only n-1 edge there. Only n-1 edge. Yeah, and there's only one unique path from from one city to another city. There's only one unique path. Yeah, for sure. Because you draw out any tree, you find that definitely that is always the case. Yeah. So is it you are using something redundant to find out the solution, that making you to need to take more memory or more times to execute? Or is there a more efficient way to find any solution? Maybe I let you think about it first. Yeah. So that is the purpose to learn. Rather than I tell you there's a particular solution, okay, you all go and do it, then definitely can solve the problem. Then you in the end you still didn't learn how to solve the problem. You just implement the solution I tell you. Yeah. So I would like to let you try. As I said, if really whole class no one can handle such a big data, I believe that so far I see most of the people can solve the 1, 2, and 4. Test case 4, I think they still manage to do it. 1, 2, and 4, yeah, still can do it. Only the third one I think is 80,000. You really need to think about the trick. Yeah, if everyone only can manage to solve the first 2 or third, the last one, then I will moderate in the end. I will moderate the marks in the end. The Q is the number of query. So if Q is 10, you expect that subsequently there are 10 lines. If the Q is 5, in the given sample input, the Q is 5. So subsequently there are 5 lines. So each line give you 3 numbers. U, V, and W. U, V, and W. So there are 5 lines to tell you. There's 5 query. That means you need to run your algorithm 5 times to find the solution of 5 queries. So you expect that corresponding there are 5 output. Yeah, but probably you should realize that it maybe not the path searching. Yeah, it is how you store the data. I think I can see some people already out of very soon you out of memory. Like I told you, that one thing I think is very obvious is adjacency metric is a problem. If 80,000 by 80,000, you probably haven't reached the point to execute your algorithm. You're already out of memory first, because 80,000 by 80,000 metric is very, very huge. Yeah, you may not be able, even you're able to create it, you may run out of time to fill out the that particular table. And as I told you again and again, is only n minus one edge. That means you put 80,000 by 80,000. Among them, only 80,000. That means it's about 80,000. 80,000 minus one element is 1. The rest, 80,000 by 80,000, the rest are all 0. But every time you need to scan and check all the 0, of course it will take you a lot of time. Okay, so back to today's lecture. I have to start my lecture, otherwise I will run out of time. So today I will talk about, today and Monday, I will talk about this matching problem. Yeah, or this is a bipartite graph. So what is the matching problem? I think I have mentioned in the very first lecture. I think in your daily life, a lot of this kind of a job assignment, or task assignment, or you can, in practice in the computer science or people working in computer engineering, you got n tasks, and then you got n computer, or you even one computer you have n core to run this m tasks. So how do you how the computer assign the job to each core? This is a matching problem. In the future you apply, you trying to select your FYP, final year project. We faculty propose n project. We have so many students. Every student, just like this example here, you maybe can select one project. You can select another project. Every student can select up to 2 projects. Then how do we do the matching? At the back end, actually they need to do the matching to match the student, and then every student of course only can get one project, and the one project only can assign to one student. We don't wish that there's a project there are 2 students receive the assignment, or one student can assign for 2 projects at the same time. So we need to optimize to ensure as many people get assign the project as much as we can. So that is a matching problem. And if you formulate into a mathematics problem, it is a graph problem. So we trying to, that means we have a graph vertex V, and can be partitioned into 2 subsets. One is, let's say it's a J subset. There are n vertex. Then another W is another m, the remaining vertex. Then J and W are 2 disjoint sets, and we want to find every edge connect a vertex in J to one of the vertex in W. So such a graph will form is a bipartite graph, like what you see here. Or maybe I have a better example, or maybe in the next slide. So the matching problem is trying to find a subset of edge that are mutually not adjacent. Just like what you see here. There's no two, they all are sort of independent. There's no 2 edges are mutually adjacent. There's no adjacent. I mean, they're not somehow connected to it. Or like if it's so-called mutually adjacent, is like Tom assigned to cutting, Harry also assigned to cutting. Then there are 2 edges are mutually adjacent. So in this kind of configuration, they are mutually non-adjacent. And that means that there's no 2 edge have an endpoint in common. There's no same endpoint. No edge have the same endpoint. So how can from this to this, how do we find this matching? So there is a matching. So the problem is trying to they're trying to find the matching solution with the maximum number. We wish to get to let as many, but of course this is a very good situation, but sometimes in the end we can end out that certain job no one assigned to particular job because no one select it, for example, or certain person can't get the job assignment because we very obvious is like if I have 2 job and 3 person, you definitely no way to let everyone get the job in the end. So that is the objective we want to achieve in the matching problem is we want to get the matching with the maximum number of edges. Yeah. So how can we do this? So this problem, the solution you will find that is similar to is a maximum floor problem. It's equivalent to a maximum floor problem, or I would say it's a simplified, because I'm not consider all the edge are only used once, only can use once. All these edges only can use once. Yeah, you are not allowed to use. That means the weight of each edge is either 1 or 0. Either there's an edge or no, there's no edge. So I'm not considered the weighted one. So it's a simplified, one of the simplified. The solution actually can solve. The solution I'm going to introduce to you in the next few slides, they can solve more complicated one, which means that I can solve the problem, the edge with the weightage. But here my problem, I only want to solve the matching problem. Actually, my weight only 1 or 0. Okay. Then first to solve this problem, this is the just now I mentioned that you have 2 disjoint set, that means J and W. So J is, let's say here in this example, I have 5 vertex, J1, J2, J3, J4, and J5. In W subset, I have W6, 7, then W8, and W9, 4. I have 4 vertex. So here, I trying to introduce another 2 new vertex. One is the source, another one is the sink. So all the source will connect to all the J1, J2, J3, J4, J5, all the vertex in the J subset. Then there's a T is a sink. Then all the W, the vertex in the W will be connect to the T. Okay, so that form a floor. So my matching problem now is I need to find the maximum floor from the S to the T. From the S to the T. Then so you can think that this one all the weight is 1. Yeah, the weight is 1. But here I don't need to write because it's either 1 or 0. If it's 0, there's no edge over there. So here you can see J1 is connected to W6. J2 is to W6 and W7. J3 is to W7, 8, and 9. Then J5 is to the W6 and W9. This is the given. The question, I want to find the maximum matching. I just need to find the maximum floor from S to T. How to do that? There's this is the solution. It can be solved by this Fockerson method, and it is an iterative improvement strategy. This is another strategy I want to introduce to you. There's a way. The thing is like iterative improvement. Later you will see this particular, to find the solution is like they slowly find one solution, find one path, then you can, after that you update the graph and then carry on to find the second path, then you will get better solution. Then you, after you update your graph, then you further find another solution, then the result will getting better and better and better and better. Eventually, when you cannot find any new path further, that is the best solution you can achieve. Then you stop. So it's a kind of an iterative improvement strategy. Yeah. So it's proposed by these 2 persons, Fogg and Fockerson, in 1956. It's a quite old approach, but it's quite useful. in our daily life, because we always encounter a lot of this kind of a matching problem we need to solve. So it's a kind of an iterative. The idea is an iterative find an additional flaw, yeah, in the network or match. Once you find a flaw, you find that it's trying to find a match from the J to W in this example. And so by doing this, yeah, important is first I need to introduce a new network. This is considered a network. Network, I mentioned sometimes they call network, sometimes they call graph. So here I call this is a network. So this is a network. So I need to introduce a complete sort of a complement, is a residue network, which is I'm not really using this original graph to find the solution. I need to introduce another network, which is look like, later you will see it, which is look like this, but yeah, but we call it is a residue network. Okay, then this residue network actually is this graph yeah, this particular original network minus the path you found, how it work, let's see. So initially there's no any new flow. I haven't started yet. So the original network is exactly same as the residue network at the beginning. So imagine you have two network, something like this. So in the Fulkerson method is trying to there's a loop, every iteration I trying to find an augmenting path. That's mean I'm trying to search a path from S to T. So you can use breadth first search, you can use depth first search. You should not have any difficulty to. Probably I will choose to use because I just need to find a path. So probably I will try to use the depth first search to search the path. Let's say I found this particular path, then they name it as an augmenting path P. Yeah, from S to T. This is one of the path I can find in the graph. So in the residue graph, so initially this is the original graph, this is the residue network. Then yeah, initially is, as I mentioned, when there's no network, they are exactly the same. After you find the first path from S to T, let's say this one, from S to J1, from J1 to W6, from W6 to T, then you update your residue graph. You update your residue network. So I will just make it in the opposite direction. Yeah. So to just make it as an opposite direction. So this is the updated after the first augmenting path found. Then I update my residue graph. This is the result. Originally, it should be something like this. Then now the difference is here, which I highlight, is this one is in the opposite direction now. Okay? Yeah, once you understand this, every iteration, you keep doing this. So initially, you have this. Initially, this is the network graph. This is the initial residue graph. As I mentioned, when at the beginning, there's no any flow. Before I introduce any new augmenting path, any flow, they are exactly the same. This one and this one are exactly the same. After I find the first path, which is from here to here, after I find the first one, I need to update the residue graph. Yeah. So that is the algorithm. Later I will show you further. So that is the algorithm of the Fulkerson. So initially everything is 0. So you initialize all the flow. Initially there's no any flow. I haven't start find. The iterative improvement strategy they use is in this part. They're trying to iteratively improve. Every time they found a path. So when they're doing this in this, as long as I can find, before I execute this while loop, I need to find a path. You can use breadth first search, you can use depth first search to find the path. So once you find the path, then you here I trying to along the path, they're trying to find the weight of the minimum weight along the path. But in this particular, this is the general fault forecasted algorithm. But here you expect that your problem, your matching problem, is either 0 or 1. Along the path, the minimum is 1. Must be 1. Must be 1. Yeah. Because there's a path that's in, it cannot be 0. Must be have, yeah, there's in the minimum also is the maximum. It only can be 1. Yeah. So this one is something, yeah, for your part, for your the question we discussed here, we don't need to bother so much. Definitely is 1. Then next is like 2 things I need to update. Of course, you found the path, you need to knock down, you need to add this particular new path into your flow. Yeah, that is my output. And then the next 2 line here, this 2 line is trying to update the residue. So update the residue is like UV, they were -1. As I said, this one definitely, this particular C minimum path, this C minimum definitely is 1. C minimum is 1. Here, definitely is 1. Because my matching problem, there's no weight, either 0 or 1. So this one definitely is 1. If it's 0, that means no edge already. Yeah. So that means after you minus, so it's definitely is 1 minus 1. So become this, for this direction will become 0. That means no, you remove the edge. Then take notes here is UV. So then for the VU in the opposite direction, I introduce a new edge, which is in the opposite direction. So yeah, should be a non-zero. Definitely is 1. I would say for our problem here, I only considered is is only 0 or 1. So there's an edge or there's no edge. So after you find the path, the next thing, of course, you need to remember this is one path. That is this part trying to do. And then you need to update the path. Here I need to update the path along the path in the residue graph. I update the residue graph. Okay. Yeah, that's why I said this C minimum is always 1. Is always 1 for matching problem. Then after update, you should get this. Take notes. I don't know whether you can see the direction change. Now it's pointing this direction. Yeah, originally the residue graph is from S to J1. Then now it's become J1 point to S. Yeah, this is important. Why? You can see why I need to do that. Because if after you do this, next iteration, I'm start search another new path. Definitely, this particular one won't be able to be searched. This particular path definitely won't be searched one, right? Because you definitely will, because you need to travel from S to T. You need to from here to here. Then you cannot, this is totally in the opposite direction already. So it's prevent you to select this particular path. You already find one match, which is J1 match with W6. Yeah, so this is the role of this residue graph. The residue graph is playing the role trying to help you to hold the information of the remaining residue, remaining matchable path you can have. Yeah, so I still have a few more options. Maybe J2 can do W6, W7, J3 can go to W7, W8, W9. J4 is a problem here, there's no match. Then J5 can go to W6 and W9. Yeah. Then I carry on. I find the next path from the residue graph. I find this is the new path. Then I update it again. That is one iteration. I update. So the next iteration, you can see that after this second iteration, we found the second path. From here is one, and from here is another one. we found two paths. You can see here I indicate in red color. 1, 2, 2 already. Then carry on. This is the third one. Okay. Yeah, the key will be the next one. Yeah. Okay. If that is okay, then the next one, after you update, you will find that the next one, what is the next path you can find? You will find that the next path in this particular residue graph will be from here to here, from here to here, and from here to here, and from here to here, and from here to here. This is the only, right? Okay, maybe I trying to clear. You can see that no other, because you can see this one already in definitely you won't choose this. You use breadth-first search, depth-first search, whatever matter. You either on the next path, next possible path you can choose is either from S to J4 or S to J5. Of course, S to J4 cannot be, no more. So you cannot reach T. The path you can reach T is from S to J5. Then J5, if you choose this one to, yeah, then you cannot. If you choose J5 to W6, W6 cannot reach T. So definitely this is not possible. You only can from J5 to W9. And from W9, you want to go to T, you definitely have to go through W3, J3, and then J3, you go to W8, and then from W8, you can go to T. You can reach a T. So this is the path. This is the last path you can have in this particular residue graph. And then when you update, that is the interesting part. When you update the flow, you'll find that this is, you will find when you find this is something like I cancel one. Originally is this one, J3 is trying to match with W9. Now you find that it's not correct. So from this path, they're trying to cancel, trying to remove. I need to remove the J3 to W9. So I need to remove the J3 to W9. And then I need to introduce, at the same time, I definitely introduce another one. Because you want to find a path from S to T, you definitely will cancel one, you need to introduce another one. So just nice that J3 will point to, will connect to W8, will match with the W8 instead of W9. So you will update the maximum your flow. So these two edge will be updated. So this is the one in the algorithm here. Yeah. When you find a path, they will try to check if the UV is the edge, then they will add. But if there's no edge between the VU, there's no edge, then they will remove a flow in the opposite direction. If there's UV, there's no edge, there's no edge. Yeah, actually there's no in the floor, there's no from here to here, there's no edge from W9 back to the J3, right? There's no, only have the J3 to W9, there's no W9, so it's not an edge. W9 to J3, there's no edge here, there's no edge from W9 to J3. You only have J3 to W9, but you don't have the W9 to J3 in the network graph. If that is the case, then you were trying to -1. That's when you will remove that edge. You will remove that particular edge in the opposite direction. So that is how they cancel this particular match. Then you will find that they definitely will introduce another new edge. in the other place. Yeah, which is J3 to W8, which is this one. Then this one, they were trying to introduce. They need to update it. So this one will cancel. I need to remove. Yeah, this one. After that, you expect the flow, this flow, okay. This one in the next edge. Yeah, you will update. So you are trying to match the J3 to W8. Does this algorithm work only with the directed graph? It's a flow. So yes, because you need to you're trying to match is trying to match the subset. You're trying to think that you're trying to flow. It's like you put the water or something like that. The flow will flowing through from S to T. So it's from the it's a directed graph. You make a directed graph. Of course, this one can solve a lot of problems. So actually, matching problem is just one of the simplest one, and which there's no weight. And then you just want to simplify match all the J vertex in J to the vertex in W, as many as you can. As many as you can. You want to find the maximum match. And what does it mean? This means that it can have multiple solution with the maximum match, but I just need one of them. The solution may not be unique. The match, the exact match, whether it's J1 match to W6 or then J2 match to W7 or not, it may not necessary. But I concern is like in the end, I have 4 matches. That is the maximum I can have. Not surprising lah. You can see J4 don't have any connectivity with the W. J4 definitely cannot find the match. In the end, only J1, J2, J3, and J5 found the match. So that is the maximum match. 4. Will there be a chance if it will accidentally flow into? No, it won't be. And if that is the case, then means it's your algorithm problem. Because you find that, if you observe in, maybe in this example, the key is the last one. Yeah, the last one is this part, is the interesting part. You'll find that when you only left this situation in your residue graph, again, it's like you need to make sure that in the algorithm, you are trying to find the path is in the GF. GF is the residue graph. Where I said, residue graph is the residue graph. I'm finding the path is in the residue graph. Only in the residue graph, in this particular graph, did he provide the information about the remaining possible match you can have. Yeah, these are the remaining so-called, the residue graph is trying to tell you is like the remaining possible match you can have. Then, and if I want to let J5 match with W9, you find that very naturally, there's a path is from here to here. Is what does it trying to do? He need to cancel this. He need to remove the match between J3 to W9. You need to remove one. Because originally, in the earlier iteration, I already find a match J3 to W9. To get a better, more match, then I need to change the match from J3 to W9 to J3 to W8, which is from here to here. Because that will give me more. I can get a better result. Iterative improvement strategy. You will find that you will iteratively improve. If they find that J5 must match with must match with the W9. Naturally, this particular path will give you the information. You need to cancel. It can be cancelled more than one. If you expect that okay, this example don't have, I can cancel another one, definitely will match another one, and then I can cancel another one and then match to another one, then eventually go in. If that is the case, not in this example, yeah, you will find that you will update all the matches, then you will get more match, then it still will form a path, because you move in one direction, back, forward, back, is cancel one and then introduce another new one. Yeah, you definitely is in this situation, then you have a chance to form a path from S to T, right? Yeah, this is something you need to think about it. So do all the solution give rise to the maximum floor? Yes. So that's the match particular, whether it's J3 match with W8 or not, it may not be, but the number of matches, the maximum is definitely this algorithm only can ensure that you get the maximum number, but the path, the exact match, it may not be unique. It may not be unique. That also can explain why that always student, yeah, when when in the future you apply your FYP, you find that the system not bother so much that you must ensure that you get what particular project or not. He's trying to ensure is they're trying to let as many students get a project, as many project as they can. They get the as many match as possible. They don't, unless they introduce other things beyond than this. Otherwise, they're only trying to find the best match. The more match, rather than they give you the best match. Then today, if I assign you to your second choice, then I can let another person have a chance to get his second try. Probably I will do that rather than I let you get the first choice, because if I give you the first try, I may end up that certain person cannot get anything. Then in that situation, they may force you to take the second choice, such that the other person have a chance to get the right a project. Because objective is everyone get the a project in the end. Yeah, that is their objective. Not let you get the first choice is what their main concern. Their main concern is all the students register for FYP, they can get the project, right? So that is the problem. So like in J3 through in many J3 in through many arrow to W7, W8 and W9, are those considered a path? Cause the arrow is already reversed after the first path. It is in the take notes. When I finding the path, you look back to the algorithm, you finding a path from S to T in the residue graph. I only look at this particular, every time I only look at this particular residue graph. Take note that these residue graph are not exactly same as the network graph anymore. Only at the beginning they are the same. Subsequently, they are not exactly the same. Okay, back to your question. Your J3, you can go to W7, W8. After this stage, you already cannot, from J3, you cannot reach the W9 directly. So when they move, they find the path from S to T. So and I move the path along here, I only can go here. I have to go to J3 and then passing W8, then I can reach a T. That's the only path. If I go to W7, I cannot reach T. I won't be able to reach T. There's no path for me. Then I go further higher, go to J2, W6, also cannot. So your algorithm definitely won't be able to lead you to this direction. You will definitely from W8 then go to T and stop. You will find that the result of this particular path is trying to ask you to cancel this match, introduce these two match. So each arrow technically can be used one. Yes, in this particular matching problem. In this particular matching problem, my each edge, my weight only 1. My weight is 1. So this C minimum, I think I mentioned, yeah, is always 1 for matching problem. For matching problem. Of course, this particular, I need to let you know is this particular algorithm can solve more general network problem, which means that each edge they may have weighted directed graph. It can solve weighted directed graph. Yeah, but here my problem is only a matching problem. It's relatively simple. My weight only 1 only. So you will find that from here, once you minus 1 will become 0. There's no edge, no floor already. So in other words, is you are right. I only can use it once. Yeah, because once I use it, the next moment they were in the opposite direction already. So yes, based on this algorithm, but that can be different problem already. It probably is not such a matching problem. I mean, this algorithm is not only solve the matching problem. It can one of the it's just like one of the problem it can solve is matching problem. It can solve a lot of other problem in weighted directed graph. Okay, so in the end, you get this is the maximum match, and you find that from the residue graph, you cannot further find any path from S to T anymore. After you update it, yeah, you only left one here. Yeah, then cannot I cannot move already. So no more, no other solution. Then you can stop. You found those are in red color is the solution. That's it. Yeah, this one you need to think about it. So maybe Monday I will clarify again. So summarize for today lecture. Yeah, this is I introduce a fault focusing method. I have to highlight that I only show you the example I show you just now is solving the maximum matching problem. But such an algorithm also can be solving the maximum flow problem. And why this thing is invented in the 1956 is during that period. It's a Cold War. Then Russian all this they trying to find the maximum flow. How the railway network, they need to find the maximum flow in the network, and then they put the bomb in that particular point. Then they will damage the host. They need to find a path. I think this is the path. Yeah. So they find that if they put the bomb along the path, this particular path, they can disconnect the whole network from in the Europe network, railway network. Yeah. So they trying to use this is they're trying to find the solution to find out that where is the maximum flow. So if I attack that particular viewpoint, it's good enough already. Yeah. So finding the augmenting path, the key is you need to find every iteration you need to find the augmenting path. Then you can use breadth first search, depth first search, or any traversal algorithm you can think of. It's fine because I just want to find a path to find from S to T. Yeah. Then matching problem is much more simple. It's like the weight is either there's an edge, then it's 1. If there's no edge, then of course it's 0. Yeah. So the implementation can be simplified much more compared to the maximum flow problem. And application wise, for maximum flow actually I don't know whether I can still can, maybe nowadays I don't know whether they already updated. Let me try. In the PowerPoint if you're trying to use your PowerPoint, you're trying to remove the background, then you can introduce some point. Let's say I want to keep this bus. Area to keep. This one. Why cannot keep? I want to remove. Let's say I want to remove this, remove this, remove this. Yeah. Actually, okay, what I want to tell you that actually this implementation, they is trying to fill the network that you click, you select a few point you want to keep, and you want to select a few point you don't want to keep. They're trying to they're trying to cut is a kind of a maximum floor algorithm to find out the cut. Yeah, actually is yeah, some people working in Microsoft research last time in 2004 they develop. After that they implement in the your PowerPoint. Yeah, for you to remove the background. So after that you can remove the background. You can select the point you want to keep. Yeah, maybe nowadays they already improve more advanced using the AI algorithm, but in the early year, yeah, they are using this max floor problem algorithm to solve it, to solve and improve. And the complexity is the challenge. I think I put it in the notes. You can find that there are a lot of way to find the path. Then you find a lot of way to find a path, then the complexity can be improved. Yeah, from time to time, people were trying to think different way to search a path. Then you can get a better, faster better time complexity algorithm for fault focusing. Yeah. So why can't we use? So okay, so maybe I this is the today lecture. I think I will release the tutorial, the last tutorial, the last lab, and the assignment by today or tomorrow. Okay, I trying to sort out the things, and maybe this question I just let you hear. I just find it today. It's quite interesting. They will let you think. It's kind of a interview, job interview question. Maybe Monday I will discuss with you. Yeah. In the meantime, just let you think about it and answer some question before I end today's lecture. So each age have a technical only once. Yeah, this one I think I answer. So the weight, okay, can be two. Okay, why can't we use the backtracking algorithm like the equine problem to find the path? You backtracking, that means you find that backtracking. How are you going to find the backtracking? Can you use the backtracking algorithm? You trying to select this one because they you need to know the network. One thing is you need to know that not they can double, like just now the J1 and W, the J and the W, they may not all you can, it's not try all the combination. It's depend on the given graph. They maybe J1 can connect to W6, may not. Yeah, it's not ask you to brute force try all of them. It's not ask you to brute force try all of them. Yeah, not necessary to try all of them. In fact, the network itself, in day one, there's no connection. Yeah, you not even need to try. You really go and brute force try all of them. But the problem is that you find the match, then the next one you cannot. Then you need to know whether the alternate. The interesting is like the fault focuser can help you to know that you can remove this one, and then this one should match with another one, will be better. Yeah. Will it be somehow backtracking? I'm not too sure whether you can simply use so-called the backtracking only. Yeah. Because this one is also kind of they help you to cancel one and then introduce, but immediately from the network they can, from the residue graph, the key is the residue graph, immediately can tell you that there's another match, you can replace it. And it can tell you that whether this is possible or not possible. If you cannot find the path from S to T, that means that is not possible. Then they won't choose it. Yeah, because you cannot but every time the augmenting graph, augmenting path can help you to update all the match. Okay, so this problem I just left here for you to think about it. Monday I will discuss with you, and probably Monday I think I will still go through this algorithm again. You can think about, you can review it again. I think, yeah, this one I think need to think about. Yeah, I think I agree that there's some it's a bit complicated. You need to think a bit. It's not use the original graph. It's trying to, in short, it's trying to, you need to introduce a residue graph to assist you to monitor what what other option you still remaining to try. So when you find a match, you update one match, then you need to remove that one. Then remaining one, from that you find the solution. Sometimes at the beginning, maybe you make a wrong decision, costing you subsequently you cannot find the match. So you need to correct your earlier one so that your subsequent can get more match. That is the idea behind. Yeah, and that is the interesting for that one. So why can't you completely remove the arrow instead of reverse the? I need to reverse because at that moment I may not be correct. So when I reverse, it indicate that you will find that when why I need to, that is like, if you don't reverse or remove then you definitely won't be able to find any match for the J5 to W9 because there's no if you don't have this particular one. If let's say you remove this one, so-called you don't reverse, you remove this one, then when you run until the fifth iteration, you're trying to find a path from J5 to W9, you stuck. There's no path from S to T, no more, because you remove this particular one, you won't be able to find the path already. When the reverse is like today you select, then the reverse is like in the future they allow you to unselect. But when you unselect, you find that this kind of a matching, you definitely on the other side you will select another new one, which is J3 to W8. Okay, maybe I stop here to let you think about it. Then maybe Monday I will talk about this topic again and discuss the last question. I left it here today on Monday. This give you to think about it. Yeah, and maybe I will summarize I will give an overview for all the topic we discussed so far on Monday. Maybe Wednesday I will make it as a consultation times through the Zoom to let you ask a question. Okay. And if there is no match from J5, if there's no match, I need to go back to this. If there's no match to J5 to W, can we backtrack to J3? You have to. If there's no match from J, there is no match to J5. Why there's no match? From J5, there's a J5 to W9. If there is no, then we can backtrack the J3 and try the J3 with W8. Well, you probably can, but very soon I believe that you will end up, that is the algorithm. You can see that this algorithm is trying to help you to do that. And you don't need to try W7. You look at this result, you will find that you don't need to try the advantage of this one compared to yours one, you will go and try the W7. Because from that W7 maybe is another solution. Only after you find the match, you find the J2 already select W7, then you cannot select it. Then you only have W8 is the only choice. And you slowly you'll find that you still need to use a fork focusing. Fork focusing is do what you are thinking and sort it out for you already. You can slowly think about it, your solution. I would say that you slowly derive all the constraint you need. You will understand why you always need a residue graph for you. Like I said, you need to consider how you decide W8 or W7. I think I roughly know what you are thinking. You think about it. Why? How do you know it's W8 not W7? And how do you prevent that J3 select W7 as an alternate match? Okay, maybe Monday we discuss about it. You can refer the lecture notes and think about it. Okay, if no other question, we discuss again on Monday. Okay, goodbye.